Yes, share screen. Can you see my screen now?
Yes.
Okay, sounds good. Okay, last week, we talked about the force, equilibrium, moment. Now, we are gonna take this forward a little bit, one step forward, actually. Today, we are gonna talk about the load types, support reactions, and simple structural systems. Actually, in these first 3 weeks, we are talking about the basics of statics and the strength of materials, which is for the next term. We are gonna do the strength of materials course after the statics, but these are the basics of all these courses. If there's a problem, if you have trouble in these subjects, believe me, you will have troubles in the next stage. That's why you have to get better understanding of all these subjects at the beginning. These are simple. I'm trying to explain all these concepts as simple as I can. Please try to understand. If you have any comments, any questions, please let me know. Send me an email, and I can think about what I can do for you at that stage. So let's get started. Load types, support reactions, and simple structural systems. Oh, here, yes. Okay, here we have load types. Here, just a second. Okay, load types. We have 2 brands here, concentrated load and distributed load. Concentrated load is like a point load on top of one point. Distributed load is a distributed load as its name. I'm going to show what they are. Let's have a look at the concentrated load here. For example, pointer options. Here, you can see a beam, a steel beam between 2 columns. On this beam, there is a crane carrying a load here. So this is my structural system, as you can see. If I draw here the free body diagram, this is the beam, which is steel beam. These 2 arrows goes up, which are the columns supports to this beam. So on top of this beam, there is a W weight, which is this one. So this load acts on this beam on one point, as you can see. This is not a distributed load all along the beam. So this is a concentrated load. We show the concentrated loads with only 1 arrow, as you can see here. This is a kind of concentrated load. We have only 1 arrow here. If this location changes, for example, there are wheels here. If this weight moves here, what we are gonna do? We are gonna, just a second, pointer, arrow options. How can I right screen? Just a second. And then presentation again. Let me visible. Why I have a problem to write on the screen? Just a second. I'm trying to understand. Pointer option. I have only just a second. Arkadaşlar bir saniye şunu ben bir anlayayım. Neden ekrana yazmadığını şu anda. Pointer. Farklı bir bilgisayarda anlatıyorum da bugün size. O yüzden bunun ayarlarını bilemedim bir anda. Niye ekrana yazmadan anlamadım. Şöyle yapalım bir saniye. İzninizle. Tekrar açalım. Şuradan. Açsak ne olur? Buraya yazabiliyor muyuz? Enable editing. Şunu yapalım. Şunu takarsak çözülecek herhalde. Tamam. Çözdüm arkadaşlar. Tekrar geri geliyorum. Sizin de ekranı kayda devam ediyormuş zaten bu arada. Sorun değil. Okay. Okay. Yes, here, if we move the location of this W, for example, it comes here. As you can see, we are going to put an arrow at this point. So we show concentrated loads with arrows. Okay. In the free body diagram. Here, let's have a look at a new structural system. Here we have two columns at both sides of the beam, and beam is here. This is our beam. You can see totally that we have a beam. So there are two floor beams connect to this main beam. This is the first one. This is the second one, as you can see. So these floor beams takes all the loads from this. This is the floor covering. So live loads, people or furniture or other stuff are staying on top of this floor covering. So this floor covering takes all the load and transfers to all these two floor beams, and these two floor beams transfer the loads to the main girder here, to this point and this point. Let's have a look. This beam, it's here. As you can see, this is the main girder. This is the main girder. We have two beam forces which are coming from these two floor beams. So these floor beams gives a concentrated load, a point load to this main girder. As you can see, this is, we are showing these forces with arrows. As you can see, the first arrow is this one, the second one is this. So if we have a point load on a structural system, if we show it with, if we can show it with an arrow, this is a concentrated load. Okay, this is a concentrated load. So here we have distributed load. Distributed load, as you can understand from the name of this loading, distributed. There is a loading on the beam along a distance. Okay, it can be all along the beam, the total length of the beam, or this distributed load can be on a part of the beam. It's possible. I will show you some different examples. Here you can see at the right-hand side, you can see a steel beam. On the steel beam, there is a concrete floor slab. Concrete floor slab. So when we check this out, you can see concrete floor slab is every point on the beam. So the thickness is same. We have the same concrete weight on this beam. So we have a uniform distributed load, as you can see at the left-hand side. How we can show it? You can see this is the steel beam. This floor load is, as you can see, because there is no change on the weight of the concrete here. That's why we have distributed at each point of this beam, we have same loading. At each point of this beam, we have same loading. That's why we show this type of loads, distributed load, yayılı yük. Okay, distributed load in Turkish is yayılı yük. Concentrated load, tekil yük. Okay, I'd like to say the Turkish words. If you have a look to Turkish books, you're gonna see these wordings. Concentrated load, distributed load. Did you get the point, differences between this concentrated and distributed load so far? Any question about this or any comment? Okay. I will show you different types of distributed loads. But firstly, let's have a look at load system. Here, I'm gonna give you an example from a real life project and then how it behaves or how we see this real problem in our calculations. I would like to show it. As you can see here, show you first. I'm gonna change the pointer. As you can see here, we have an abutment or a support system at the left-hand side and the right-hand side. Between these supports, there is a beam. There is a beam, as you can see. On top of this beam, there is a soil load. So there is a soil, sand. Okay. We are carrying a soil with this beam between these two supports. So if we have a look this structural system, between these supports, we have a spacing, which is L0. How we are gonna convert this real structural system to our calculation system? I'm gonna show this to you here. You can see here, this is the spacing L0 between two supports. And also, this beam sits on top of this support at this point, here and here. You can see dark points here. From the face of this support to this point, we have a distance, which is A/2. The total stink area is A. This length is A. We are stink at the half point of this width. So that's why we have A/2 at this point. And it's same for the right-hand side. So the main span, the span of this beam is between these two dots. So what is this length? L0 plus A/2 plus A/2. As you can see here, this is the structural system of this beam. I show this beam with a line, as you can see here, which is a blue line. This is a support triangle. This is another support, We are going to talk about the types of these supports in the next page. Don't think about what is these small circles here, what is these shadings are here. Don't think about this one. Okay, just try to understand how we convert a real system to our calculation system. So we have just checked, or we have just calculated the support spacing. Support spacing is between this dot and the other one, this one. Okay. So as you can see, this spacing is L equals L0 plus 2 times A over 2. Okay, 2 times L over 2. This is the calculation spacing of this beam. So on top of this beam, there is sand load, as you can see. At each point of this beam, we have same sand thickness or soil thickness. So at each point, we have same load, same soil load. So it's like distributed load, because we know that at each point of this beam, or let's change the wording, if we have same loading at each point of a beam, that means we have a distributed load. That means, or uniform distributed load. You can see here at the bottom side, this part, the red part shows the uniform distributed load on top of this beam. Okay, a load is coming from top, and this beam takes all these loads and transfers them to these two supports, A and B. So half of this loading goes left, half goes right. That's okay. If we are talking about equilibrium, so at the end of the day, our beam is sitting here safely. That means there's an equilibrium. Otherwise, we are gonna fail. If there is no equilibrium condition, or if there is no balance, our system will fail. We know that. To provide the equilibrium, for example, please look at the circle A at the left-hand side. The support system at the bottom gives a reaction. Let me change this pointer. Just a second. All the load goes from here to this point, and load goes from here, and the other half goes from this point. So remember the action-reaction principle we talked in the first week. Etki tepki, action-reaction principle. So if I give a vertical reaction here, this support gives back a vertical reaction, but in opposite direction. So you can see here, these are the support reactions. These are the support reactions, because if these support doesn't give a reaction, this system fails. That means there is no support over there. There should be something. If you are standing on a floor, your weight goes from the floor, from your feet, and the floor gives back the same amount of support reaction to your feet. Otherwise, this system fails. Okay. This example shows us how we convert the real structural systems to our calculation models. The bottom side, you can see our calculation model. At the beginning, we have a three-dimensional beam. We convert it a line. We have a soil load on top of this beam. We convert it to distributed, uniform distributed load. At the left and right hand side, we have supports. We convert them to triangles, as you can see at the bottom. So this is our model at the bottom. Okay. Here now we are gonna talk about the uniform distributed load. You have to know these parts as your name. Otherwise, you cannot solve anything. These are really basic, really easy. But when you try to make some applications, you cannot use these methods. Don't understand the logic behind that. If we have a uniform distributed load, we are gonna do some calculations with using these distributed loads. Okay. In the next stage, we are going to calculate support reactions. It's important for us in this course. Support reactions. And we have a structural system. On top of this structural system, there are different loadings, whatever. I'm going to ask you, what are these support reactions? So, these support reactions are important. Next term, we are going to use these support reactions and we are going to draw the internal force diagrams. It's a next step. But beforehand, we have to understand how we can calculate the support reactions. To do it, we have to understand how we can use distributed loads. The first one is uniform distributed load, which is the basic one, which is the easiest one. Here you can see the blue line is my beam. On top of this blue line, I have a uniform distributed load. Uniform distributed load is represented with many arrows, as you can see here. We have, you can see many arrows. Number is not important. Okay, number of these are not important. Don't try to count these arrows one by one. Okay, these are nothing. This is a sketch. But what I understand, I have same loading at each point. The magnitude of this load is Q. The distribution length is L. Okay, I have a uniform distributed load. To make a calculation, this is a rule you have to know. To make a calculation, I have to convert this uniform distributed load to a concentrated load. Okay, I have to convert it to a concentrated load. It's really basic. The total, okay, I have a distributed load all along this length L. I have to convert it to concentrated load. So I have to calculate the magnitude of this this concentrated load. How we can do that? Please take a look at the shape of this loading. The shape of this loading is like what is this shape? Basically, what is this shape? Are we there?
A rectangle?
Yes, it's like a rectangle, right? So we are going to calculate the area of this rectangle. Area. What is the area? So here, this length is the magnitude of uniform distributed load is Q. This length is L. So the area is Q times L. The area of this uniform distributed load gives me the magnitude of the concentrated load. Okay. Okay, if I convert this uniform distributed load to concentrated load, the magnitude of the concentrated load is area of this distributed load. Okay, this is the first thing. And the second thing, where is the location of this concentrated load? So if I have a rectangle, the center point of this rectangle is my location, the concentrated load location, I mean. So let me change the color. Just a second. Pink. So I have this rectangle, the center point is here. Center point is here. Total, if the total length is L, L over 2 and L over 2. This is the center point. The total magnitude is Q times L. The location of this concentrated load is important for my calculation. In the next stage, I'm gonna calculate some moments. I'm gonna write some moment equations. That's why the location is important. Remember, to calculate moment, we use the force and the distance. I mean, force times perpendicular distance gives me moment. So in the next stage, I'm gonna do this calculation. That's why the location of concentrated load is really important here. But you get the point, I guess. If I have a uniform distributed load, the area of this shape gives me the magnitude, and also the location is center of this rectangular shape. Okay, this is the uniform distributed load. Okay, we have different shapes. We have triangular distributed load. As you can see, this is a kind of loading, starts from a 0 magnitude, goes up to maximum, and then we are here 0 point, goes up to maximum, and then goes down to 0 again. This is not a uniform distributed load. At each point, the loading changes linearly. As you can see, this is linearly, goes up and then goes down here. But the logic is same. If I have a distributed load, its magnitude is the area of that shape. In the previous example, we had a uniform distributed load and the shape is rectangle. Area of that rectangle gives me the magnitude of that force, that distributed load. Here, what we have a triangle, as you can see. We are gonna calculate the area of this shape. Area of this shape. What is it? So the bottom length is total L. As you can see, Q times L over 2. It's same from like this. That gives me the area of this triangle. This is a symmetrical triangle, as you can see. At the left and right hand sides, I have same loads. So the magnitude is QL over 2. Where is the location? Where is the location? As you can see, if this is a symmetrical triangle, the midpoint of this triangle is my location, my concentrated load location, actually. So this is easy to understand. Any question for this symmetrical triangle? Okay. I guess after you take a look all these subjects by yourself, you're gonna raise your questions. Send me your questions if you have. Okay. But as I reminded at the beginning, if you don't understand how you can convert all these loads to the concentrated loads, you can't do anything. You can't solve any problem. That's why please try to understand what we are doing here. Let's have a look to the right-hand side. We have a rectangular perpendicular triangle. Sorry, perpendicular triangle. What is the rule? What is the magnitude of this loading? Area of this triangle. It's basic. The rule is rule here. If we have a distributed load, to convert it to concentrated load, calculate the area. It's basic. Q times L over 2. That's okay. Here. Hope I can see on the screen. Okay. This is times L over 2. This is the magnitude. This is basic. But here, be careful. Watch out. We need to find its location. We are using here 1/3 rule. 1/3 rule. Actually, this is not about a statics course. It's about the geometry. I'm just using the geometry rules here in my calculations. I'm not doing a new calculation. Okay. The center point of a perpendicular triangle is, or let me, is 1/3 L away from the highest point, because we have the highest loading at this point. The location is 1/3 of the length. This is L over 3. That means L over 3 away from the highest loading. For example, if I change the question, let me ask you a new one. For this is 6 meters. Okay. If I have a loading like this, what is the magnitude of this concentrated load and location? Where is the location?
It's 12, I guess, and it's 4 meter 4 metrelerde bir gösterebilir miyim?
From which side? From left hand side or right hand side?
This is 4, this is 2.
Yes. Okay. Okay, you're right. Good. The rule is same. Calculate the area. 4 times 6, 24 over 2. You know, it's 12. Okay, if we know the magnitude is 12. The location is, remember this rule here, 1/3 rule, from the highest loading away L over 2. So this is totally 6. L over 2 is L over 3, sorry, is 6 over 3, which is 2, this point. Here is my concentrated load, which represent this distributed load. Okay, I think you get the point here. If we go one step forward, trapeze loading here. Up. How we can clear your writing here? Can you do it, please? Oh, thank you. Here you can see a trapeze loading, basically. So this is not like a triangle. This is not like a rectangular. So at each side we have a loading value. For example, at the left-hand side we have Q1. At the right-hand side we have Q2. So we have to convert this loading to basic concentrated loads. Otherwise, we can't do any calculation. So what we are gonna do, we are gonna split this trapeze shape to basic shapes that we know about the area and location. Here you can see if we split it two pieces, the green part is a rectangle, as you can see, and the red shaded area is a perpendicular triangle. So we have one trapeze distributed load, and then split it in two shapes. That means at the end of the day, we have two concentrated load, one for the triangle, one for the rectangle. Take a look at the rectangle, the green area, calculate the area, Q2 times L. That's okay. This is the magnitude of this green area. Where's the location? Location is the midpoint of this rectangle, L over 2. Okay, from left-hand side and the right-hand side. So let's have a look at the triangle. So I'm gonna, this part is Q2 because we divided it. So what is this part? This part is Q1 minus Q2, right? Okay, the rule is same. Calculate the area. Q1 minus, the area is written here. Q1 minus Q2 times L over 2. What is this? This is the area of this red shaded area. Can you see this area easily when you take a look at this trapeze shape? You'll have to see this one. This is basic. Divided two basic shapes and calculate the area. This is the area of triangle. So the location, the load location is really important here. What was the rule? From the highest loading point, go back L over 3. So the total is L here. This part is, as you can see, L over 3. So you can, now we have two concentrated loads on our structural system instead of one trapeze distributed load. That's okay. No worries. We can calculate all these complex loadings easily. So these are the distributed load types. Okay, what you have to know here. The first one is magnitude of a distributed load to convert the concentrated loading. We have to calculate the area. That gives us the magnitude. And we have to find the second thing, we have to find the correct concentrated load location. The rectangle is basic, triangle is, the symmetrical triangle is basic at the midpoint. If we have perpendicular triangle, we have to use 1/3 rule. From highest point, 1/3 L away. our concentrated load location. So if we have complex shapes, we are gonna split it to basic shapes, and we are gonna calculate their concentrated load separately. That's okay. We don't have to use only one concentrated load. If we split it 2, 3, I don't know, 4 basic shapes, at the end of the day, we are gonna have 4 different concentrated loads. That's okay. But you have to find 4 concentrated load locations depending on these geometrical rules. Yes, these are the trapeze distributed, distributed loads actually. Now we're gonna talk about the support reactions. Here, as you can see, we have different supports. We have roller support, we have pin support, and fixed support. We have 3 types of supports. We will talk about them one by one in the next stage. But if this part is a book definition of this support reactions. Okay. Support is in Turkish mesnet. Mesnet. Support reaction is mesnet tepkisi. Okay. Mesnet tepkisi. Support reactions. If a support prevents translation of a body in a given direction, then a force is developed on the body in the opposite direction. Why? Because we have action and reaction principle. If a system gives loading to a system in this direction, this loading comes from the system. Let me change the color. Is this better? Okay, the red arrow comes from the structural system. The structural system is this. I don't know what it is, but you can see a structural member. The support reaction is not this one. Support reaction is the support gives back a loading in the opposite direction. So this is support reaction. Okay, this is the support reaction. Similarly here, if rotation is prevented, a couple moment is exerted on the body in the opposite direction. So it's same. If we prevent the rotation, the support develops a moment in the opposite direction. This is the support reaction. We have 3 types of supports. We will talk about them one by one. The first one is pin support. Pin support. Here, as you can see, we have pin support. At the top right corner, you can see a photo from the Harbour Bridge from Sydney. So Harbour Bridge support the support points, as you can see. Support point is this. Let me, I'm sorry, here. This part is totally support. So the loading comes from here, from this structural member, and goes to the ground, and support gives back a reaction. This is support reaction. Okay. Now, what is the rule for this pin support? Pin support. If we have pin support, we have two support reactions. Okay, one vertical, one lateral. So we show this pin supports in our calculation with a triangle, as you can see here, right hand side, and this shaded part at the bottom, triangle and shaded part, or we can show only this. We can see only this. So what we said, if we have pin supports, you have to know this one. There's no other solution. You have to know the number of unknowns. We have two support reactions, which are unknowns. We are going to calculate in the next stage. We have two unknowns, vertical reaction and lateral reaction. As you can see, VA, vertical A, and HA, horizontal A. As you can see here. If we have pin support, we have two unknowns, we have two reactions. These reactions are unknowns, bilinmeyenler in our calculations. Firstly, we are going to calculate these support reactions, and then after that, we are going to keep going to our calculations. So what we have two unknowns for the pin support. Let's have a look to next stage. Roller support. Roller support. Here, at the top right corner, you can see a steel beam with a roller support. Roller support, as you can see here, this is a real life structure. This is a support point. At the bottom, there are a few wheels here. These are steel members. If there is a wheel at the bottom, so our beam can move in the horizontal direction. If it can move, that means there is no reaction because there is no obstacle which prevents this motion. It can move, so there is no reaction in the lateral direction. But all the weight vertical loads goes from the bottom to the foundation, and this foundation gives back a reaction, as you can see here. So this is support reaction for roller support. So if we are talking about roller support, we have only one support reaction in vertical direction. Okay, in vertical direction. We show this in our calculation. We show this roller support with triangle and with these circles at the bottom, which represent the wheels, like this real example. Or sometimes in some books, you can see this like this. There is a line a little bit bottom side of this triangle. There you don't see a circle here, but you see only a line a little bit away from the triangle. These show us the roller support. Roller support have only one support reaction. If we have an inclined surface, by the way, the support reaction in the roller supports is always perpendicular to motion direction. So if I'm in the lateral position, as you can see here, this is my system. Our system can move in this direction. So my vertical support reaction is perpendicular to this. Or take a look this example. I have an inclined surface, as you can see here, with a slope. Okay, my motion is parallel to this inclined surface. So my reaction is gonna be perpendicular to this motion, to this surface. So rule is here. Oop. If we have roller support, what we have to know? We have only one reaction, or I mean, we have only one unknown, which is the vertical one. The one direction is the motion direction. It's free to move right or left or which direction you want, but perpendicular to this motion, we have our vertical reaction. We have to know this one. Okay. Okay. Here we have fixed support. This is the last support type we are going to consider in this course. As you can see, fixed support. Please look at the photo at the top. As you can see, this part is a cantilever system, konsol veya çıkma in Turkish. In Turkish, the engineering term is konsol. This point is a fixed support for this cantilever member. As you can see, sorry. As you can see here, this is my cantilever member. So at this beam, depending on the loading condition, I will have three unknowns, three support reactions, one vertical, one horizontal, and one moment support reaction. Okay, we have to know this. If I have a fixed support, I will have three unknowns. Ece, sesini kapatabilir misin? Ece, duyuyor musun bizi? Ece, duyuyor musun bizi?
Hello.
Ece. Okay. Teşekkürler. Yes, we were talking about the fixed support. We have three unknowns. Okay. Question for you. If I have a roller support, how many unknown I have?
One.
Yes. In which direction?
Vertical.
Yes, you're right. If I have roller, in Turkish, kayıcı mesnet. Kayıcı mesnet. Roller support is kayıcı mesnet in Turkish. Pin support, sabit mesnet. Pin support, sabit mesnet. fixed support, ancastre mesnet, ancastre. Okay. If we have pin support, how many unknowns we have?
Two.
Two. Which are they?
Vertical and horizontal.
Okay, you're right. And if we have fixed support, we have three, as you can see on the screen: vertical, horizontal, and one more moment. Okay, we have three support reactions. Okay, we are going step by step at the beginning. When you take a look these supports, they may seem to you meaningless at the moment. We are not using them. We are just learning them, what they are. But in the next stage, we are going to use them in our calculations, basic calculations. So you will get better understanding of these supports or how we are going to use them in calculations. Okay. What time is it now? It's 11:05. Before to go ahead, I think let's have a break now, because we are going to start to structural system. I don't want to split that part. Let's have a break, half an hour. We're going to be here at 11:35. Okay. And then we will keep going to next stage. Okay, guys. See you. Okay, ladies and gentlemen, we've just talked about the support types: pin support, roller support, and fixed support. Now we're going to talk about structural systems. The first one is simple beam. Simple beam. Simple beam is, as you can see at the top, there is a beam which is a bold line, as you can see, bold black line. And at one side, we have pin support. At the other, we have roller support. So this is a simple beam. What should we have? So if we have a simple beam, there should be a pin support and roller support. Not two support or not two roller support. One pin, one roller. Okay. So in the second here, in the second sketch, you can see the free body diagram of the this simple beam. Here we have a pin support. Pin support. Remember how many unknowns we have? We have two unknowns, two support reactions. We put two support reactions here. And for B, which is roller support, we put here only one support reaction. This is our structural system. So we have to calculate this HA, VA, and VB. How we can do that? We have three equilibrium equations: total X, total Y, and total moment equals 0. Or if we write all these three equations equal 0, we can get HA, VA, and VB. Okay, these are the support reaction calculation. And here, what we learned, what is a simple beam? If we have a simple beam, that means we have one pin, one roller support on each end of this beam. Okay, let's have a solve an example. Here you can see we have a simple beam, pin support, roller support. On this beam we have an sloped concentrated load. Its magnitude is 100 kilonewton, and its slope is proportional to 3, 4. Here is 5, 5. So here we are looking for the support reactions. Okay. The total span is 6 meters. The location of this concentrated load is 4 meters away from the left support. So what we have? We have three equations, but at the beginning, let's have a look this concentrated load. Actually, we like to study with perpendicular forces. We don't like these type of inclined forces. It's not easy to solve. So if we have if we have distributed load, we convert it to vertical concentrated load. If we have inclined forces like this, we resolve it to its perpendicular components. Depending on given slope, we resolve this 100 kilonewton to two different forces, which is 80 kilonewton in the vertical direction and 60 kilonewton in the lateral direction, horizontal direction. Now we resolve this given force to these two forces. That's okay, we have it. Then we have three equations here. Actually, if you write the total MA, by the way, I'd like to, maybe I didn't say it. Here for the pin support, you can see two support reaction. That means moment is 0 here. There is no moment for pin support. It's same for the roller support. We have only one reaction and moment is 0. But here for the fixed support, we have two lateral and vertical forces, support reactions, and also one more moment. Moment is not 0 for the fixed support. Okay. In this question here, let's calculate the total MA. Total moment at point A equals 0. Why? Because it's the pin support. It can rotate, but it can't move. So the moment at this pin support is 0. So in this direction, 80, by the way, let me write on the screen, pointer option 10. Okay, I have 80 here, 80 times 4, which turns the system in this direction. This force turns the system in this direction. So I have vertical B. Vertical B turns the system in this direction. What I did, I assumed this moment is positive. This is positive. So the opposite direction is gonna be negative. That's why I have here a minus. Minus VB times 6 meters equals 0. So I'm using here the moment equation. From this equation, I have only one unknown in this equation, so it's easy to calculate. VB is 53 kilonewton. That's okay. Then total y equals 0. In vertical direction, total y on this beam is 0. Vertical A is in the, this is positive side, this is negative side. Total y equals 0. VA goes up to positive direction. And we have 80 kilonewton goes down to the negative direction. So here we have minus 80. And then VB is in the positive direction, it's plus. So what we have, we know what the VB is from here. If we put it here in equation, we are gonna get VA, which is 27 kilonewton. And total X on this beam. Have a look the sketch again. How many horizontal load I have on the beam? We have two. One is HA, the other is the 60 kilonewton. So HA in the positive X direction, 60 is in negative direction. HA minus 60 equals 0. Remember, we are doing vectoral calculation here. The directions are important to solve these problems. So as you can see at the end, we have 1, 2, 3, three support reactions solved, and all they're positive. If I get a negative direction, that means my assumption is, direction assumption is wrong at the beginning. We will talk about these issues in the next stage. Here, I just want to show you how we calculate support reactions. We have 3 equations to solve for each type of system. Cantilever beam, console kiriş. We have only one support and one free end. As you can see, left-hand side. Here is fixed support, here is free end. Okay, this is free. This part is fixed. This part is fixed. Here we have a load P, as you can see, which is an inclined force. And in the midsection, as you can see, we're drawing free body diagram. Okay, instead of this support, we are putting support reactions to the end, left end, and you can see the unknowns, vertical A, horizontal A, and MA, moment A at the moment. So these are the unknowns. How we can calculate them? On this beam, if we write total X, total Y, and total M equals 0, we can calculate all these unknowns. Okay, here we go. This is an example to explain the situation briefly. Here you can see there's a cantilever beam. On top of this beam, there is an inclined P load, which is 120 kilonewton. And its location is 3 meters far away from the left support. What we have, we have inclined force. We are gonna resolve this inclined force to the perpendicular components. Okay, vertical and lateral. If we have this 3, 4, 5 triangle here with the proportion of these numbers, you can calculate the vertical force is 72 kilonewton and the lateral force, the horizontal force is 96 kilonewton. Let's have a look at the support part. Support is at the left-hand side. What we have, we know that if we have a fixed support, we have three unknowns. We have three unknowns. Don't forget this one. We are gonna draw the positive directions of these forces. Positive directions of these forces. That's okay for us. The vertical, for the top side is positive for the vertical A, arrow goes up. The right side is positive direction for horizontal A, and the moment is going up, it's positive direction. Okay, now we draw the support reactions and we're gonna write the equilibrium equations, total MA, total MA. If we write total moment around for point A, as you can see, the point MA, which is the moment on the point, as you can see, MA, and what we have 72, which occurs, which makes a moment on point A. So this turns the system in this direction, rotates the system in this direction. 72 times 3. So when we look here, this moment and this MA, they're in the same direction. That's why this is positive, as you can see, equals 0. So if we do this calculation here, MA is minus 216 kilonewton meter. Minus. What does this minus mean? It means here, my assumption, my direction assumption for MA at the beginning, at the initial position, is wrong. It's actually in the opposite direction of what I assumed. So as you can see here, the moment MA is in this direction. This is the positive direction. But no worries, you can accept one direction at the beginning. If it's wrong, the result has minus. We know that in vectorial calculation, minus means the opposite direction. So I know that this moment goes in opposite direction, goes in this direction. Okay. This is for MA. Let's write total Y. Total Y. VA in the vertical direction, what I have, VA and 72. We have only two forces. VA is in positive direction, goes up. 72 goes down. VA minus 72 equals 0. So from here, VA is 72 kilonewton, but it's positive. Its direction, assumed direction is correct. Correct? So VA is positive. And total X equals 0. In the lateral direction, in horizontal direction, we have HA and 96. HA is in positive, 96 in negative. So HA minus 96 equals 0. HA is positive 96 kilonewton. Okay. Any questions so far to calculate these basic support reactions? Okay, I guess no. Okay. Overhanging beam. Here we go. We have a simple beam actually, but at one side there is a cantilever part. So we call this type of beams overhanging beam. When we look at the support reaction, one is pin, as you can see, one is roller. Remember, this is roller. There is a space between this line. Sometimes we put here some circles, sometimes we don't. This means roller support. Also, this is roller support. Okay. In this example, we have a vertical 300 kilonewton and a sloped 240 kilonewton at the right end of the cantilever. At the beginning, before to start any calculation, what we are going to do, we are going to resolve this sloped force to vertical and horizontal components, depending on the given proportional numbers, 3, 4, 5 triangle, as you can see. So if we solve this 240 kilonewton here, we have vertical and horizontal components. And for the left hand support, you can see we have a pin support. So that means we have two unknowns, horizontal A and vertical A. I put all these support reactions in positive directions to my sketch, to my free body diagram here. This is my free body diagram. Okay. Here in the second support, I have a roller support, so I have only one reaction, which is vertical. You can see BB here. Now we have my calculation free body diagram. So I'm gonna do examples. I'm gonna do the equations here. Let's write the total MA. That means total moment at point A. Here we can write this force 300 rotates the system in this direction. So moment is 300 times 3. And here I have 192, which is vertical, turns the system in the same direction, and the total distance to the point A is 6.5. That's okay. But I have here vertical B. Vertical B rotates the system in the opposite direction. That's why the moment here is negative. VB times 5. The distance is 5. VB times 5 equals 0. So in this equation, I have only one unknown, which is VB. So we have this equation and one unknown. It's easy to calculate VB, which is 429.66 kilonewton. Okay, let's do total MB0. The total moment for point B is 0. Let me change the color here in color. Here, I'm going to use green for the MB. Okay, the point is here. Okay, rotation point is B. Now, vertical A rotates the system in this direction. Vertical A times 5. Vertical A times 5. Then, that's okay. This is I assume this is the positive direction. Now we have 300 times 2. This 300 rotates the system in this direction. So it's negative. As you can see, we have minus. So 300 times 2. And what I have 192 kilonewton. This turns the system rotates the system in this direction for this. Is it positive or negative? So this is the rotation point. The first positive rotation direction is this. So this arrow follows the positive direction. So it's positive. 192 times 1.5. So we have the total MB equals 0. In this equation, we have only one unknown, as you can see here. It's easy to calculate. You have your calculators and you can do this calculation. So vertical A is 62.4 kilonewton. Okay. Now we have vertical A, vertical B. If we have a look the free body diagram, we have one more unknown, which is HA. To calculate that, let's write the total X, total X. In the X direction, we have HA and we have 144 kilonewton. Let's write it HA, which is in positive direction, minus 144, which is in negative direction, equals 0. So HA, we can calculate HA here. HA is 144 kilonewton. So as you can see here, we have just calculated the these support reactions for this overhanging beam. Yes, to check if what we did, if we are doing right or wrong. What we use here, we use total M0, total X0. We have all unknowns at the moment. That's okay. You don't have to do more, but to do it to understand if we are doing right or wrong, we can write total y equals 0. Okay, total y equals 0. Let's write it. Let's write it. This is a check. Okay. I always suggest to do this. I do it myself for my calculations. I do many calculations. I can make any mistake while I'm doing my equations. So this helps me to understand if I'm wrong or correct. Total y. So in the sketch, total y, let's have a look sketch. We have total y. What we have in the y direction, we have this one. This one, vertical B, and this. We have 4 forces. So vertical A minus 300 plus vertical B, total Y. Let's write it here. Op, what I'm doing. Equals VA is this, minus 300 plus VB and minus 192. If this is okay, if this is 0, yes, I'm doing correct. So if you do this calculation, it's 0. So my calculation is correct. I was doing same thing here. Okay. Okay. We talked about the load types, support reactions, and simple structural systems so far. I'm gonna do some applications for you to get better understanding. Okay. Now, here we have a simple beam. simple beam. How we can understand simple beam? If we have a beam, only one stick or member, and one support is pin support, the other one is roller support. Okay, here is like that. On this beam, as you can see, we have an inclined 5-ton and a uniform distributed load, which is 2-ton meter. Okay, 2-ton meter. First, in the first step, what we are gonna do, we are gonna resolve the inclined force to perpendicular components, and then we have a uniform distributed load. We are gonna convert it to a concentrated load. And also we're gonna write the support reactions to the free body diagram. Okay, let's have a look at the bottom sketch. As you can see here, we have inclined force and its components, 5 cosine 30, which is lateral or horizontal component, 5 times sine 30 is the vertical component. That's okay. Let's have a look at the uniform distributed load, the magnitude, the concentrated load's magnitude is area of that force. Area is 2 times 3, which is 6 ton. And its location is midpoint of that rectangle. So 1.5 meter to the right and 1.5 meter to the left end of the force. That's okay. And also you can see vertical A, vertical B, and horizontal B. Here, why we are doing this? At the left-hand side, we have a roller support. So we have only one unknown, which is VA. At the right-hand side, we have a pin support. That means we have 2 unknowns. We have VB and HB. In this bottom sketch, we draw everything to my free body diagram. Here, as you can see, let's write the equations, equilibrium equations. Let's get started from the X. Let's calculate the HB. Total X equals 0. So you can see in the X direction, we have a lateral force, which is in positive direction. HB, I don't know if HB is positive or negative. I don't know at the beginning. So I select the positive direction, positive X direction. That's it. So 5 cosine 30 plus HB equals. So if we solve this equation, we are gonna get HB equals minus 4.33. Minus, that means my direction is negative. HB in actual direction goes to left-hand side. Okay, but no worries. This is correct. This calculation is correct. So I have a minus here. That's okay. We have a moment A equals 0. The total moment of all these forces around the point A equals 0. So let's write the moment for this point. For the point A is here. Okay. Let's write forces. VB times 6. VB times 6. I assume that. Let me write screen again. Pointer option 10. Pointer option in color. Here, the vertical B rotates the system in this direction. Here. So minus 6 times 4.5. 6. Now I have this concentrated load. I convert this uniform distributed load to this 6 tons. I don't need this uniform distributed load. Put on here this concentrated load, and its distance to the point A is 4.5 meter, but it rotates the system in negative direction. That's why here we have negative. So we have next this force 5 sine 30 rotates the system in negative direction. That's why it has negative as well, times 4.5 here, distance to the point A equals 0. So in this equation, as you can see, we have only one unknown, which is VB. So it's easy to calculate what the VB is. VB is here 5.13 tons. Okay. Then we have total MB equals 0. So here VA times 6 minus 5 times sine 30.4.5 minus 6 times 1.5 equals 0. So here we have only one unknown, as you can see, which is VA, and it's 3.37 tons. So now we have all unknowns, all 3 unknowns. To check it, let's do the total Y. Total Y, take a look at all the vertical forces on the system. Vertical A goes up, minus 5 sine 30 goes down, and also the 6 tons, the concentrated load coming from the uniform distributed load goes down, which is minus, plus vertical B equals 0. So here, from this equation, vertical A plus vertical B is 8.5 tons. We have just calculated vertical A and vertical B. Let's sum these numbers. If they're equal to 8.5, the result is correct. Yes, 3.37 plus 5.13 equals 8.5, which is coming from the equation one line above. As you can see, VA plus VB, it's correct. So our calculation is correct here. Okay, here we have another example. We have a simple beam. As you can see, one support is pin, other one is roller. On this beam, we have a vertical concentrated load and a trapeze load. Here, now we have to convert this trapeze loading to concentrated loads. What we were doing for trapeze loadings, we are gonna split it to basic shapes. The easiest method is to split it to one triangle and one rectangle. So here we have one rectangle and its area is 3 times 3, 9 kilonewton. And for triangle, what we have 2 kilonewton meter times 2 times 3 meter over 2. So it's 3 kilonewton. So I have 2 different concentrated loads coming from this trapeze loading. The 9 kilonewton at the center point at the midpoint of the rectangle. That's okay. As you, this is the center point of the rectangle. That's okay. But here we have a perpendicular triangle. So its location is 1/3 L from the highest point. Total length is 3 meters. So here is 1 meter from the highest point. We have the magnitudes and also locations. By the way, I'm gonna write, this is 10. 1, 2. Okay. On this beam, we can write the total x. Total x. There is no lateral horizontal loading, so HA, the horizontal component, is here 0. There is no lateral load, as you can see here. Okay. Then total total MA is this point. This is point A. Total MA, 10 times 1. 10 times 1. Only here, you have to watch out for the rotation directions. Okay. We are doing a moment calculation, which is force times distance. That's okay. But you have to be careful about the rotation directions, which direction you assumed positive or negative. So here in this example, here we have this direction is positive. And then we have this 9 times 4.5. It's in this direction. That's okay. And 3 times 5. It's in this direction. Okay, it's positive. But we have vertical B. Vertical B is in this direction. So turns the system like this. So it's negative. Vertical B times 6. That's why here we have a negative. If we do this equation, you are gonna get this number, 10.92 kilonewton. This is VB. Okay, let's write the moment B equals 0. Moment B, we have one unknown again, vertical A times, let's change color here. Let me change pointer. Oop. Here. Oop. This turns the system in this direction. This is positive. And 10 turns the system in this direction. This is negative. And all these are negative, as you can see here. Negative, negative, 4, 3, negative. Only positive is this one, the first one, equals 0. Here, if you do this equation, you're gonna get the vertical A, which is 11.08 kilonewton. You know, we have 3 equilibrium equations. We've just used only 2 of them. We can use the last one to check our calculation. Total y equals 0. If you write the total y equals 0, vertical A and vertical B in the positive direction, which are in positive, minus 10 goes down, minus 9 goes down again in negative direction, and minus 3, which is in negative direction, goes down, equals 0. So here, what we get, vertical A plus vertical B equals 22 kilonewton, as you can see at the bottom. So vertical A and vertical B should be totally 22. We have vertical A and vertical B values. We can sum these two numbers. If we get 22, that's okay. We are in the right way. If we get a different number, oh, that means we made a mistake in the previous calculations. We have to check them out again. Okay. Okay. Here we have a vertical cantilever and also two more cantilevers running out from this vertical cantilever to the left and right hand side. As you can see on this loading system, I have a lateral triangular loading and a vertical triangle loading. By the way, why while we are converting these distributed loads to the concentrated loads, please consider that there is no meaning for the arrow numbers. Don't count anything else like this. Just a second. I'm trying. Let's change the color. Just a second. Here, for example, we have this one, this one, this one. These arrows doesn't have any meaning. They only show there is a distributed load here. It's triangular. That's it. Because in the previous year, in the exams, many of your friends, for example, did this. For example, if I have a uniform distributed load for 3 meters, this is 5 ton meter. Okay, what did they count the arrow numbers 1, 2, 3, 4, 5. 5 times 5 equals 25 ton. But actually it's 5 times 3, it's 15 tons. Okay. There is no meaning for the number of these arrows. It's a sketch, it's just a drawing to represent that there's a distributed load here on this region. Okay, keep this in your mind. Just calculate the area of these basic shapes. Okay, let's go back to our question here. In our question, we have two distributed loads. Have a look to right sketch. One is in horizontal direction. If we calculate the triangle's area, we are going to get 3.83 tons. That's okay. The magnitude here, this is coming from the area of this triangle. That's okay. And its total height is 4.5 meters. We need its location. Remember, from the highest point, 1/3 rule, divide this to third and get the exact location here. If we divide it third, we are going to get 1.5. This point is 1.5 meter from far away from the highest loading point. As you can see, we get the magnitude and location. That's okay. We convert this triangular distributed load to concentrated load. Let's have a look at the top loading here. As you can see, we have 1.5, which is the maximum loading. 1.5 times 3 over 2 gives me the magnitude, which is 2.25 ton. Okay. It's here, and we need the magnitude. We need, we need location. this span is what? 3 meter, 3 meter. And what, again, remember the 1/3 rule, divide this third, which is 1 meter, far away from the highest loading point. Yes, we have the location at the moment. And let's have a look to support. What kind of support we have? We have here a fixed support. That means we have 3 unknowns. 3 unknowns, 1 vertical A, 1 horizontal A, and 1 more moment A. Okay, here, let's write the total X, We have total forces on the system. As you can see here, 1 is HA, 1 is this. There is no more 1. And let's do it here, HA plus this and this are in the same direction, they are in positive direction, equals 0. So HA here is negative, as you can see, negative. That means HA is in the opposite direction. But no worries, if I have a minus here, I know that means the opposite direction. Yes, we have 3.83 tons. Let's have a look to y direction, total y equals 0, which is the vertical direction, vertical A minus 3 minus this 3 is in negative direction, and 225 is in negative direction, minus this part is 225 part equals 0. So we have only one unknown here, VA equals 5.25 tons. So we have HA and VA. So we have one more unknown, which is MA. Okay, we are gonna calculate the moment at point A. I have MA, which is the direction. I assume this direction is positive. And 3. This 3 is here. 3 is here. 3 times 1.5. Rotates the system in the positive direction. That's okay. This is positive. Minus here. Minus here. I have this force. Rotates the system in negative direction. This is negative. And also I have this lateral loading, rotates the system in this direction, which is negative direction, because positive direction is this. This is positive direction, goes right side. The negative is going left side. Here you can see 3.83 times 1.5 equals 0. So if we do this equation, we are gonna get MA, which is 3.50 ton meter. Okay, ton meter. So here we have 3 unknowns, and we have just calculated all of them. Any questions so far regarding this example? No. Okay. We have 2 more examples, and then we have 3 pages, I guess, and then we are gonna close the session today. Here, as you can see, a beam system. We have 2 beams here. Between 2 beams, we have 1 more beam. We have a beam system. How we transfer this P load to these supports? That's the kind of question. The location of this is the secondary beam. These are the primary beams. Okay, between the supports. But the secondary beam is between these primary beams. That's the differences here. The location of this primary, sorry, the secondary beam on the primary beams, as you can see, 4.4 meter and 5 meter here. Its location from support to this beam location 4 meter and 5 meter. That's okay. We are gonna calculate support reactions one by one. The P is here, 270 kilonewton, which is here. We know that this load is distributed to point A and point B here. How we distribute it? We are gonna take this out here. This is the secondary beam as a sketch. We have one primary beam here at the left-hand side, one primary beam at the right-hand side. Okay, I know here and here we have primary beams, but what I did, I convert this part to a simple beam to make calculation. What I assumed, one side is pin support and the right-hand side is roller support. That's okay. That means I have two support reactions at the left-hand side, one at the right-hand side. Okay. And I write the concentrated load here, and I write all the distances to here. Here, as you can see, there is no lateral loading. If you write total X is 0, this HA automatically is 0. Don't think about this HA too much. There's no lateral loading on the system, so the HA equals 0. What we have now? We have vertical A and vertical B. Vertical A and vertical B. How we can calculate this vertical A and B? If we write the total B, I can calculate vertical A. If I write the total MA, I can calculate the vertical B. So we are gonna let me write the equations here. Total MA equals 0 times 3 minus VB times 9 equals 0. If we do this calculation, VB equals 90 kilonewton. So if this is 90, you can calculate in the same way VB, VA as well. So we can get VA and VB. Okay, what is VA? VA is the point load at this point. VA is, and VB is here. Vertical load. All these are. Okay. So now we are gonna take out the primary beams one by one and calculate their support reactions. A, if we have the first beam you can see here the vertical load and its location and distances. And with the same methods, the moment method, you can write total MC equals 0 and total MD equals 0. You can calculate VC and VD. I'm not gonna do the same calculation here one more time. You can do it by yourself. If you have a trouble, please let me know. VC is 100 kilonewton, VD is 80 kilonewton. Here we have HA, but this is not HA actually. This should be HC. This is point C. HC, it's 0. Why? Because there is no lateral loading on the beam. Total X directly is 0. This is the first primary beam. Let's have a look at the second primary beam. Remember, it was 90 kilonewton. As you can see here, we have 19 kilonewton, HE, VE, and VF. We have the HE equals 0. As you can see, there is no horizontal loading on the beam. That's okay. You can write total ME equals 0 and total MF equals 0. Let me write them here, just a second. Total ME equals 0, total MF equals 0. And with these equations, you can solve this VE and VF. Let me write the same for the top. MC equals 0 and MD equals 0. With these equations, you can calculate all the support reactions. Okay, any questions so far for this example? Did you understand what we are doing? We are trying to calculate the support reactions C, D, E, F here in this example. But there is a secondary beam. So firstly, we have to share the load P between the two primary beams. We did it at the first step. One takes 180, one takes only 90 kilonewton. After that, for each primary beam with their loading, we calculate support reactions. We assume each primary beam is simple beam, and we did these calculations. So that's all for this question. And today, our last question is this. It's about roller support. Actually, it's about the inclined roller support. We have, as you can see, a simple beam, but right-hand side, the roller support is inclined. So on the beam, there is an inclined sloped 300 kilonewton. You can see the left-hand side, HA and VA. At the right-hand side, we have an RB. Why RB is like this? Remember the rule for the roller support. The support reaction is perpendicular to motion direction. Okay, so my motion is in this direction. It can go up and down, whatever, but it's in this direction. So you can see here RB. RB is perpendicular. RB is perpendicular to this motion, and its slope is depending on the this surface slope. We have what we have. Okay, we resolved the 300 kilonewton to its perpendicular components. That's okay. HA and VA. Here also, we resolved this RB to perpendicular components. Okay, perpendicular components, and we get two reactions chopped here. Actually, for roller supports, we have only one support reaction. That's okay, which is RB. Okay, RB here. We don't have any support reaction in the motion direction. That's okay. But RB is in a sloped direction. So depending on the slope, I convert this RB to perpendicular components, VB and HB. That's why we see here two components. Actually, there is no two components for roller support itself. We have only one, which is RB. We resolved this RB to two perpendicular components here. That's why we have two different. So at the end, we have these forces. You can write MA, total MA equals 0 with these numbers. So here, vertical B is 144 kilonewton. Total Y equals 0. As you can see, total Y, we have VA, VB, and 240. We know what the VB is, 144. So in this equation, you can get VA. VA is 96 kilonewton. If we write the total X here, we can get HA, as you can see, 288 kilonewton. 288 kilonewton. We have VB, VA, and HA. So we have VB, okay, but what is RB? We are looking for actually RB, not VB. As you can see here, there is a here RB is in this direction. There is a proportion with this 3, 4, 5 triangle here. To calculate RB, you can use these proportional numbers, 5/4, which gives us 180 kilonewton for RB. RB is this. If you like to calculate HB, it's easy again. 144 times 3/4. These are coming from these proportions. Okay, these are not the special magic numbers coming from elsewhere. All they are coming from this question. Okay, now we have RB, HB, VB, all unknowns. Any question so far for this example? Yes, no. Okay, ladies and gentlemen, thank you for your attendance today. What I suggest you for this week, please have your time and take a look all these loading types, how we can convert distributed loads to concentrated loads. What are the support types and unknown numbers? How we can calculate these support numbers or support reactions, sorry. How we can calculate, please take a look at them. At the end of the day, we are going to ask a question about this subject in the exam. I don't like to study for the exam, because if you don't do this at the moment, you cannot do standoff materials course in the next stage. All these are about these support reactions, forces, and anything else. These are the fundamentals of the statics and the strength of materials. Please, please, please, if you have a trouble in these subjects, unfortunately, you're gonna fail. I don't want you to fail. That's why, please take a look this subject on time. I know if you look at all these subjects one night before the exam, you are gonna mix everything to each other. So you will not feel confidence. That's why do everything on time. Okay. Thank you so much for your attendance. Have a good weekend. Have a good day. Take care of yourself. See you next week, guys. Okay. Bye-bye.
See you, Professor.